Welcome back. In the last video, we constructed our 57 card Spot-It deck, and we were very happy about that. We have our whole beautiful 57 card Spot-It deck with all of these things corresponding to the lines on the projective plane over the field with 7 elements. Beautiful. Today, I want to talk a little bit about how this generalizes, because we started from the very beginning of this series with talking about Spot-It decks exactly like the one that comes in the box, where every card has exactly 8 symbols on it. And so we've stuck into that mold so far, but I want today to jump out and talk about a little bit more general. So I'm going to go ahead and define a full Spot-It deck. So I have underlined the word full here. That's really the thing I am adding, of order M, to mean that I have a collection here of cards where every card, instead of having 8 symbols, they all have M symbols, and such that no symbol occurs on every card. That was one of our requirements just for a regular Spot-It deck. Every pair of cards has a unique symbol in common. That was part of every Spot-It deck. But the thing I'm adding here, the new part, is I want every pair of symbols to appear together on a unique card. In some sense, if that's not true, that means my deck is missing cards that, quote-unquote, should be there. So we can ask lots of questions. Namely, in the very first video, I posed the question, what's special about the number 8? Well, we know how to construct, by our argument from before, full Spot-It decks for every M where M-1 is a prime power. So, note, by previous work, the lines and points of P2F form the card's symbols of a full Spot-It deck of order size of F plus 1. So the way we did this for order 8 was we took the field with 7 elements, and then that plus 1 was 8. Remember, where is this plus 1 coming from? This plus 1 is coming from the fact that I'm needing to tack this weird infinity point on every line. So the lines sort of like honestly have size of F points, like this really has 7 points, but then we had to tack on this infinity symbol here in order for it to work for parallel lines. That's where the plus 1 is coming from. And so a corollary of this, from everything we have done so far, is that if M-1 is a prime power, we know how to construct a full Spot-It deck of order M. And just to remind you, because there's lots and lots of things flying around here, where does this M-1 as a prime power business come from? This M-1 as a prime power business comes from the fact that we, in order to apply this note, need a field with M-1 elements, and there are only finite fields of prime power order. But for every prime power, there is one. So we can make these things. I'll note as a mathematical structure, the thing we're making is something that would be called a finite projective plane, this collection of points and lines that meet these properties. So basically, I've just Spot-Itified the definition of what a mathematician would call a finite projective plane. So I should note, these Spot-It decks, the ones that we know how to make, these are called the de Sargusian planes, or de Sargusian Spot-It decks, if you want. So, just as a few examples, if, say, you wanted to make Spot-It harder, and you wanted to make super Spot-It, you could make a full Spot-It deck with M equals 24 symbols on every card. And if you did that, there would be some enormous number of cards, but this would work because 24 minus 1 is 23, which is prime. So we can just use this construction, the Desarguesian plane of order. In fact, it would be called the Desarguesian plane confusingly of order 23, but whatever. We can use this construction because 23 is a prime power. In particular, it's prime. If you wanted to make a deck that was just a little bigger, you could use 9 symbols for every card, and 9 works because 9 minus 1 is 8. 10 would work because 10 minus 1 is 9. And then we run into issues if you want to make a spotted deck with 11 symbols on every card because 11 minus 1 is 10. Or 7 symbols on every card because 7 minus 1 is 6. And 10 and 6 are not prime powers. Now, please note, in no way does this prove you can't make a full spotted deck of those orders, because all we've done so far is we've proven that if it is one of these orders, then we can, and we know how to do it, and we get these particular examples. So we know how to make examples for lots of sizes, but not all sizes. So I want to prove the following proposition for you, and then I'll go on to sort of tell you the answers to some of the questions as best we know them. But the proposition I want to prove for you is that actually, if you know the order of a spotted deck, that is, if you know how many symbols are on every card, then you know how many cards are in it. So a full spotted deck of order M always has M squared minus M plus 1 cards and M squared minus M plus 1 symbols. Okay, there is no wiggle room on that. So that means that if you wanted to make your full spotted deck of order 24, then it would need to have 553 cards. Now, if they didn't even want to bother printing 57 cards, probably they're not going to release Super Spotted with 553 cards. But at least mathematically, there's no reason they can't. So I want to prove this proposition. So to prove this proposition, we're going to go in a few steps. So the first thing I'm going to do is tell you how many times each symbol shows up. Here's the lemma. In a full spotted deck of order M, every symbol shows up on exactly M cards. You might recall we proved something kind of similar to this way back in an earlier video, but now we get to prove this exactly because we have this full hypothesis, which, remember, adds the condition to all of our previous conditions that every pair of symbols now has to show up on a unique card. So let's prove this lemma. So choose a symbol. I'm going to call the symbol A. And we're going to lay out all the cards with an A. Okay, so we'll just lay them out however many there happen to be, and each of these things have an A on them. Don't know how many of them there are yet, though. Then I'm going to choose a card with no A. Now, note I can do that, again, because of my definition of a full spotted deck. That's just part of my criteria, is that there's no symbol that shows up on every card, because otherwise this is boring. And so if I choose a card with no A, let's say the card looks like this. B, C, D, however many symbols there are on it. Well, I know how many symbols on it. There are M total symbols. Now, each of these symbols has to show up on one of these cards, because, remember, every pair of symbols shows up on a card. So A and B have to be on a card, A and C have to be on a card, A and D have to be on a card, and so on and so forth. This is M total pairs. And all of these pairs have to be on a card. And in fact, all of these pairs, not only must they be on a card, each of these pairs has to be on a different card, because if, say, A, B, and AC were on the same card, well, that card has both B and C on it. And now BC, the pair, actually shows up on this card, as well as one of these cards, and that's bad. So all of these, all M pairs, have to show up on one of these cards and a different one of these cards. So that shows me that there are at least M cards with an A on it. Why can't there be more cards with an A on it? Well, there can't be more cards with an A on it, because if there were, then now that new card, it doesn't have anything in common with this card, because that new card can't have a B, C, D, etc. on it, because those are already here with A's already. So, in fact, what does that show me? There are exactly M cards with each symbol. So that's a pretty strong condition. If I know M, I already know exactly how many cards every symbol shows up on, namely they all show up on M cards. So, for example, in our full Spot It deck again, remember that every symbol, such as the 6, 0, they all showed up on exactly 8 cards, because this was a full Spot It deck of order 8. So that's our first lemma. Our second lemma that's going to go into this proof is that, in fact, in a full Spot It deck, the number of cards is equal to the number of symbols. So you might recall, for example, that in our full Spot It deck before, it came up a lot of times that there happened to be 57 symbols and 57 cards. So here is a proof of this. I'm going to let C be the number of cards. I'm going to let S be the number of symbols. And I'm going to let M be the order of the deck. So I'm going to use my usual combinatorial proof method that I'm going to write down a question, and I'm going to answer it in 2 different ways, and hence those 2 different ways are going to be equal. So my question is, how many total symbols are printed on the cards? So here, I'm talking about the number of printed symbols, not just the number of different symbols. And so, for example, every card has M symbols on it. So one answer here is C times M. So, for example, in our deck of 57 cards with 8 symbols on each card, how many total printed symbols are there? Well, there's 57 times 8. But in general, there's however many cards there are times however many symbols are on each card. On the other hand, instead of counting by card, we could count by symbol. And so also another answer to this question is to say, well, for each symbol in the last lemma, what did we say? Every symbol shows up on exactly M cards. So this number is also the number of symbols times M. So these 2 things are equal, because the number of total symbols that are printed on cards is both C times M and S times M. And so I can divide by M, so C equals S. And that proves this lemma. So the number of cards is always equal to the number of symbols, and the number of times each symbol shows up is always equal to the order of the deck, namely the number of symbols on each card. So, now we're ready to prove the proposition. What was the proposition we're proving again? The proposition we're proving is that a full spotted deck of order m always has this many cards. We're going to derive how many cards and symbols it has. So we want to show that that number is m squared minus m plus 1, and we've at least so far showed that the cards and symbols, those numbers are equal. So next, I'm going to use the fact that every pair of symbols shows up on a unique card. And I'm going to use that to count the number of cards. So how many pairs of symbols are there? Well, there are certainly S choose 2 pairs of symbols. On the other hand, every card has M choose 2 pairs of symbols, right? Because every card has M symbols, so there are M choose 2 pairs of symbols. And so what this is saying is that if I multiply M choose 2 by the number of cards, that covers every pair of symbols exactly once, while there are S choose 2 pairs of symbols. But remember from the lemma that the number of symbols is the number of cards. So I can simplify this a bit. So C choose 2 is equal to M choose 2 times C. And I'm going to go ahead and write out the algebra of C choose 2. So that's C times C minus 1 divided by 2. M times M minus 1 divided by 2 times C. Okay, I'll multiply by the 2's to clear those out. I'll divide by C on both sides to clear those out. So I'll get C minus 1 is m times m minus 1, which is m squared minus m. So C is m squared minus m plus 1. But remember, C is also S. So C is m squared minus m plus 1. And then we are done. So we now know for any particular m what we're looking for if we're looking for a full spotted deck. So we know our full spotted deck for m equals 8 had 57 cards, so that had better mean that 8 squared minus 8 plus 1, that had better be 57. 64 minus 8, sounds like 56 plus 1 is 57. Okay, yes. So this number that we got before, it was sort of written into the universe that this number for a full spotted deck of order 8 was going to be 57. But our question is still, well, is there a full spotted deck of order 7? Well, we know how many cards it would have. It would have 7 squared minus 7 plus 1, which is 43 cards and symbols. And again, I want to emphasize the logic here. 7 minus 1 is 6. 6 is not prime. And so we don't know how to make a full spotted deck of order 7. But that doesn't mean one doesn't exist. Now, as it happens, this turns out to be a question, like all questions, that is equivalent to a question that was posed by Euler. Namely, Euler posed something called the 36 officer problem. So if you're interested, you can look up the 36 officer problem and you'll find lots of fun exposition about it. It might take a bit for you to convince yourself that this is really the same question about whether or not there's a spotted deck of order 7. But it turns out that it is, in a way that you can understand if you're so inclined. Euler did not successfully solve the 36 officer problem, but later, a mathematician named Terry, that was their last name, did solve this problem and found that the answer, perhaps surprisingly, is no. So this is due to Terry. So if I write out, let's go up to, say, 15. Let's write out our possible orders of spotted decks. We want to know if there's a spotted deck of order m for each of these orders, and let's figure out what we know. So for 3 minus 1 is 2. That's a prime power, so our construction works. You can call that our de Sarguzian spotted deck if you want. 4 minus 1 is 3, that's a prime power, so there's 1 there. 5 minus 1 is 4, so there's 1 there. 6 minus 1 is 5, so there's 1 there. 7 minus 1 is 6, and I just told you, thanks to this result of Terry, this is not possible. 8 minus 1 is 7, 9 minus 1 is 8, 10 minus 1 is 9. 11 minus 1, we don't know yet. As in currently in the video, you don't know. 12 minus 1 is 11. 13 minus 1 is 12, so we don't know. 14 minus 1 is 13. 15 minus 1 is 14, so we don't know. So this one is a difficult theorem, but it's a theorem. And then these we, as of yet, don't know. Here is a harder theorem. Okay, so this is something which is called the Brooke, Reiser, Chawla theorem. And what this says is if there is a full spotted deck of order m, and m is congruent to 2 or 3 mod 4, that is, if you take m and divide it by 4, the remainder is 2 or 3, then m minus 1 is the sum of 2 squares. Let's look at this. So for example, for 7 is 3 mod 4. So what this is saying is if there was a full spotted deck of order 7, I would be able to write 6, which is 7 minus 1, as a sum of 2 squares. But if I write out the squares are 1, 4, 9, 16, 25, so on and so forth. There's no way I can add together 2 of these numbers to get 6. 1 plus 1, 1 plus 4, 4 plus 4, and 4 plus 4 is already too big. So I've run out of possibilities. So this theorem, in particular, implies this result of Terry. In fact, actually, if you dig a little deeper, you'll find that this result of Terry is actually a little stronger than just saying that there isn't this thing. But this result at least implies that there's no spot attack there. 11. If you look up to 11, then 11 minus 1 is 10. 11 is 3 mod 8. But unfortunately, 10 is 1 plus 9. So Brooke, Reiser, Chawla does not tell us anything in this instance, which is a bit of a bummer, but what are you going to do? 13. 13's not 2 or 3 mod 4. 13's 1 mod 4, so Brooke, Reiser, Chawla doesn't tell us anything. 15. 15 is 3 mod 4. 15 minus 1 is 14. Is 14 the sum of 2 squares? Well, I look here and I see that 14 is not the sum of 2 squares. There's no way to combine 2 of these numbers added together to get exactly 14. So, by BRC, no full spotted deck of order 15. Okay, so none by BRC. These questions are very, very difficult. In fact, it turns out, because when you're describing a spotted deck, there's a lot that you can do. You get to choose a bunch of symbols, and so if you wanted to, for example, talk about this case for 11, what we're really asking for is we're asking for some collection of symbols. In fact, how many symbols? 11 squared minus 11 plus 1, which happens to be 111 symbols. You're asking for a set of 111 symbols, and you're asking for 111 different subsets of these 111 symbols, each of order 11, that satisfy all of these properties. Well, as it happens, 111 choose 11 is a very big number. And so 111 choose 11 choose 111, which is really the number of things you would have to look for. To say that again, you'd really have to look at all ways of choosing 111 cards out of the possible 111 choose 11 cards. So this is a preposterously large number. And so what that means is that even to do this by computer is very difficult. Okay, this is, I should really say that again, a preposterously huge number. So it is quite a feat then that this actually was done by computer, and the answer is there is not one. But that took a lot of work. So just the act of doing enough math to put this into a computer is itself a paper that is published to say, hey, there's not one of these things. And so, no. Now, if you can conceive of how ridiculously large this number is, then maybe it's not so surprising that this number, the number that you would need to answer this question, is way, way, way bigger. Many orders of magnitude bigger. And so, since this theorem doesn't apply and the computer is too big, this is actually open. That is to say, if you were able to either produce a spotted deck of order 13, or prove that there is no spotted deck of order 13, that would be an answer to a big open question in mathematics. It would almost certainly be enough to earn you a PhD right there. And if you continue, there are lots and lots and lots more numbers where we just don't know the answer. So, who knows? That's the moral of the story. This is wide, wide open. Past the Brooke, Reiser, Chawla theorem, we really don't know. So I wanted to actually say just a little bit more about how this works out. And so, namely, what would you expect based on this information? So if, and this is a big if, but if you believe the general consensus is that there are no full spotted decks where m-1 isn't of prime power. We have admittedly very little evidence to support that, but that's the belief. We've checked it up to 11. And so, if you believe that, the natural thing to believe is, okay, maybe these ones we've constructed out of finite fields, maybe those are the only ones. So, reminder, the ones that are constructed out of finite fields, those are called the Desarguesian full spotted decks, or the Desarguesian planes, if you want the technical language. And if you want to look at it, you can check, actually, for order 3, there are only the Desarguesian spotted decks. For order 4, there are only the Desarguesian spotted decks. And so when I say that, I'm saying someone by computer, in much the way they showed that there are none that exist here, they found all the spotted decks up to this order, and they found that all of them up to that order were isomorphic to one of the Desarguesian ones, for 3, 4, 5, 6. There just aren't any for 7 at all, for 8, for 9. And so maybe you're feeling good about the fact that the real theorem is that there's only the Desarguesian full spotted decks, and that actually sounds kind of natural and believable. Unfortunately, when you get to 10, it turns out there's not only the Desarguesian full spotted deck, there are actually 3 others. So for order 10, there's the spotted deck that we know how to make out of the field of order 9, and there are 3 others. So there are 4 different ways, effectively, legitimately different in whatever sense you want, of making different spotted decks of order 10. For order 12, we know the one way, the Desarguesian way, using the field with 11 elements. We don't know any others, but we don't know that there aren't any others. And then once we get to 13, we just don't know anything anymore. So this is really in a way, the perfect encapsulation of what doing math is like. You have this guess of, well, I know how to do this. Maybe these are the only ones. And then it turns out, no, those aren't the only ones. There are these other ones. But somehow, magically, all the other ways we know of making full spotted decks all happen to construct full spotted decks where the number of symbols minus 1 is a prime power. And so, could you make one with these other numbers of symbols? Who knows? Another question you could ask that also no one knows, let's say we drop this admittedly fairly artificial assumption for full spotted deck, namely a full spotted deck. Remember, that was the additional constraint that every pair of symbols showed up on a card. What if you just say, what's the largest spotted deck with 7 symbols on each card? No one knows that either. There's some bound. It can't possibly be as large as 43, because if it were as large as 43, then there would be a full spotted deck of order 7. But who knows? So this whole area, which again I'll remind you sort of is broadly known as design theory, is rife with questions with very, very small numbers like 12 and 13, about which we just don't know very basic questions. Even the number 7, again, there's this very basic question that we don't know the answer to. All right. Thank you for sticking with this for this long. I hope you've enjoyed this. If you have any questions, feel free to ask them. If not, I hope you have a wonderful day. And until next time, be well.